The next section in this class is going to be a couplet of videos on glaciers. In our online textbook, this is chapter 14. Glaciers are a really interesting topic, but not relevant to everyone because some of us live in hot climates where we don't see glaciers. We don't see ice. We don't even see snow. But I think they're important to study for everyone. And I just want to justify that right here at the beginning with this question of like, why should we study them? I think there's three reasons. One is because of this modern climate change and the effects that the warming is having on glacial retreat. Another aspect that's critical is water supply. And finally, the third reason why a geology student should study glaciers is going to be because it's such an important landscape maker. Glaciers produce features that we see, both from an erosional perspective, where they're removing rock and material to create a landscape, to create topography, but then also depositional. And I'm going to teach you about those features in the second set of videos. So just to kind of anchor these with some pictures, here's this one from earlier in the semester showing ice mass change that has been measured. This isn't a projection here, right? So, and we see both in Antarctica and Greenland, these super ice sheets are melting, and this ice is going away to the detriment of the polar bear, but then also to sea level rise, which is something that someone like in the Maldives, which is the people there have never seen ice. They're innocent in this whole process of climate change because they don't have an industrial process that emits greenhouse gases, but their country would go away and cease to exist if all the ice on Antarctica and Greenland were to melt. More important than that is water. Take a look at this. All right, here's our blue globe that we see all the time. If we were to take away the water, this is the amount of water, where this bigger dot is salt water, not drinkable. This dot is fresh water. And what's crazy is that 70% of that dot is actually tied up in ice. So 70% of all fresh water is tied up in ice. This matters because there's places, like specifically in the Andes or in the Himalaya, where people's drinking water is coming from melting of ice. And if the ice goes away, then they no longer have their water source. Okay, so those are the justifications, I think. Let's get some definitions. We'll just start here with the basic. What is a glacier? There's going to be two types of glaciers, and both types are slow-moving. So that's not how you spell slow. So these are very slow-moving. I want you to picture something like a meter per day is the kind of rate, and it's either a stream of ice or a sheet of ice. And this is going to come down to what type of glacier this is. Critically, either type of these need to survive the summer. If you have a lot of ice but it melts in the summer, then it is not a glacier. All right, so we have to survive the summer. If you meet that definition, you are a glacier. There are two types. There is the alpine type of glacier, and these occur in the mountains, where the cold and the snow is due to high elevation. The arguably more important type of glacier, yeah, I'd say it is more important, is called a continental ice sheet. These are the big ones. These are the ones that are 2 to 4 kilometers thick, and they sit on Greenland, and then one sits on Antarctica. The one in Antarctica in particular actually covers 10% of Earth. 10% of Earth is covered by a continental ice sheet in the one in Antarctica. So how do glaciers form? Either alpine or continental. I guess I have pictures of each of these before we move to that formation. Here's a picture of an alpine glacier. You can see it looks like a stream flowing down towards lower elevation. The area up here is where there's perennial cold and excess snow and ice, which builds up and has to go somewhere, and so you flow as a solid downhill. If we look at the glaciers in Antarctica and Greenland, okay, so here is Antarctica, and again, it's not, here we go. It's not this. This is sea ice. That's a different beast. It's what is sitting on land. So this here, this is sea ice. That's not what we're talking about. We're talking about Greenland, which is right here. And if we were to look through a cross-section of Greenland or a cross-section across Antarctica, that's what these pictures here are showing. And you can see that these are incredibly thick piles of ice, and what happens is this is the highest point, right? And so things flow downhill, and so ice is flowing like this downhill towards the edges. All right, so let's go through glacier formation. This can be like a heading, and I think we should anchor this with a picture. So let's do this as an alpine. So here's our topography, and we're coming downhill, and we can add a glacier. Here's the glacier, and this glacier flows down this hill. Good. We're gonna have a couple places here. There's gonna be, and they're called zones. So up in the high mountains where it is perennial cold, this is called the zone of accumulation. Accumulation. And down here at the toe, where it is much warmer and things are melting, this is called the zone of ablation. And ablation means melting and getting rid of. Zone of ablation. We can add some definition. Let's see, do we need to add anything here? Let's just do this. Let's go zone of accumulation. And I think the word accumulation is good in and of itself. So you just need to picture that this is cold and that snow and ice is accumulating here and not melting. For the zone of ablation, this loss that is occurring is in the form of melting, but it's also in the form of calving. Calving means breaking off of a large chunk, you get like a big sliver like this at the end that then falls off. There's another piece we should add here, and it's an equilibrium line. I'm going to add this here. I'm going to put EQ. These are how glaciers talk about, or how glaciologists talk about the formation of glaciers. So equilibrium line. And the equilibrium line is kind of the middle part. It separates the zone of accumulation from the zone of ablation. And this is always moving over millennia. Because as climate changes, the equilibrium line could migrate uphill if the glaciers are in a period of retreat, or the equilibrium line could move downhill during a period of, let's say, an ice age. And so it's this equilibrium line that we could, let's say that it's a measure of advance or retreat. One key thing about this image that I want you, this is a conveyor belt of ice. It is a flow of ice. It's a bulldozer of ice. But any particle of ice is always moving downhill. So even if we're in a period of retreat, that means that the toe is moving backwards, but ice is still always flowing down. All right, so now then, to finish off there, this first lecture, I just want to talk about motion. Go to a second. Let's see, here we go. Motion. This is like a big heading. How does ice flow? Ice is a solid, but it's able to flow downhill by gravity, and it's flowing at rates of, let's say, 10 to 300 meters per year. You could find glaciers that are moving slower than that, and you can find glaciers that are moving faster than that. But as students, this is the kind of rate I want you to picture. You're never going to get run down by a glacier. I guess if you stand in a single place for a day, you could see it moving. It's about 1 meter per day at the fastest rate. And it moves in two different ways. Well, importantly, I guess we should say downhill by gravity, or down topography by gravity. And it's going to do this in two ways. One is plastic deformation, and these are actual ice crystals that are changing their shape and deforming. And then the second way is more simple, and it's called basal sliding. I'll draw each of these, And so plastic deformation, importantly, what we need to draw now is a crystalline solid. When ice crystallizes, it crystallizes in hexagonal shape. And if you were to ever see this under a microscope, you can actually see these beautiful hexagonal crystals. Well, what ends up happening is because of the shear from the downhill flow of gravity, you get this significant pressure this way, pushing you downhill, but then there's also this like frictional that's holding you back, and so these crystals start to deform, and you can imagine them changing their shape. So this is one way that they deform. This would be the slower way. It's plastic deformation of the crystalline solid. Now, basal sliding is more simple. It is exactly what it sounds like. So if we have, here is our land below, we have our ice. Here's our ice. I'm actually going to draw some cracks in the top of this ice because we're going to define these as crevasses. A crevasse is a crack in the top of the ice, but with basal sliding, here's what we should do. Let's add a little bit of water. Because this water, they're oftentimes, just like with the ice skate, ice skates slip along the ice surface because of this lubricating level of water. Well, there tends to be a little bit of water between the rock and ice interface. Rock and ice. And that lubricant allows sliding and slip to occur. Let's see, what other things can we make in this drawing? We could say, okay, we could like draw a little box here and say, this picture we just drew of the crystalline, this is showing how you can have this plastic deformation in the middle. We have, oftentimes, the downhill part of the glacier is moving faster than the uphill part of the glacier, and the differential speed allows the upper surface of the glacier to crack, and that's how we get crevasses. In fact, we should put that word over here now. A crevasse. This is a crack on the brittle surface of a glacier. If you watch an adventure movie where people are in a glaciated terrain, someone almost invariably falls into a crevasse or needs to be rescued from falling into a crevasse. Crack on brittle surface by differential velocity. The top of a glacier is often brittle, and the deeper parts are plastic. So maybe we add the word ductile. So the crevasses don't extend all the way down to the bottom because there tends to be this brittle ductile transition within a glacier. All right, that's how a glacier works. Now let's talk about how they impact landscapes in the next video.